All right, so where we left off in the last video, we were talking about inflection points in concavity. And one thing I wanted to point out, which is not stated here, but if P of, let's say, x, y is, or let's call that f of x, is an inflection point, and if f double prime of x exists, then f double prime of x will equal 0. So in a certain sense, inflection points are kind of similar to critical numbers, but for a second derivative as opposed to a first derivative. In a first derivative, we say that a number c is a critical number if the derivative is equal to 0 there, or if it's not differentiable there. In the case of inflection points, the second derivative will either not exist, and we saw an example where the function had an inflection point where it wasn't even differentiable in the first place, so the second derivative wouldn't exist either, or the second derivative is going to equal 0. And the reason that happens is because the function is going to be changing from concave up to concave down, or concave down to concave up. Our second derivative will be changing from negative to positive or positive to negative, which means it has to become 0 at the point where that point of inflection occurs. So that's important to know. But let's check out this example. It says we want to sketch the graph of a function y equals f of x satisfying the following criteria. And notice we're not told anything about f of x except for these pieces of information. We know some stuff about its first derivatives and first derivative and second derivative. So looking at this information here, it looks like some of the relevant x values are 0 and -2, because I see x equals 0 appearing here. When x is less than -2, something happens. When x is greater than -2, something happens. When x is less than 0, something happens. When x is greater than 0, something happens. So what I'm going to do is sketch my coordinate axes and just make note of those specific x values. I'm going to label them. Okay. Now I don't need to label x equals 0 because that's going to correspond with the y-axis here. But at least at -2, something important happens. So the first thing it says here is that we have a vertical asymptote at x equals 0. That's the y-axis. I'm not going to draw a line over the y-axis. We're just going to remember that this will act as a vertical asymptote. Now, it says when x is less than -2, f prime of x is greater than 0. That means positive. So what that tells me is that to the left of -2, that's where x is less than -2, our function must be increasing this whole time. But there are two ways in which a function can be increasing. Three, technically. You can have a line which is neither concave up nor concave down. You can have a function that's increasing but concave up. And you can also have a function that's increasing but concave down. Notice concavity does not determine whether you're increasing or decreasing. You can be doing either or in different cases of concavity. So we know that our function is increasing on this interval, but we need to know which of these three cases we're looking at. So in order to determine what's happening there, we have to also look at our second derivative. Now the second derivative, it doesn't tell us anything about what's happening at -2. The second derivative is talking about what's happening when f double prime is less than 0 and greater than 0. It says when f double prime is less than 0, when x is less than 0, f double prime of x is less than 0. This means decreasing, but it's decreasing everywhere to the left of 0. So, not decreasing. The second derivative being less than 0 means that we're concave down. So we're concave down this entire time. But we're also, according to this, increasing when x is less than -2. So I need my function to be increasing up until we get to -2 while remaining concave down that entire time. So that might look something like this, okay? That's concave down, but it's also increasing. Now to the right of -2, when x is greater than -2, and it says when x is not equal to 0 because we have an asymptote there, f prime is negative. So that means we now have to shift from increasing to decreasing all the rest of this time. However, we also know that we are remaining concave down for everything to the left of the y-axis. So one way of accomplishing that is to make my function do something like this. Okay, so notice we're increasing up to here, where we're supposed to be increasing, and then we're decreasing away from it, but we're concave down the entire time. Now, what happens to the right of 0? So when x is positive, our second derivative is positive. That means we need to be concave up that whole time. But if we're greater than 0, then we're definitely greater than -2, where f prime is negative. So that means two things. We're concave up because of this condition, but we are also decreasing because of this condition. And then don't forget that x equals 0 is an asymptote. This is one way of accomplishing that. Something like this. Okay? So here, notice we are concave up the entire time, but also decreasing the entire time. This will satisfy all of those conditions. And this is not the only graph that would satisfy these conditions. I could do very different, or a variety of graphs that are satisfying these conditions, but might look slightly different than what I have here. So remember, when you get a question like this, there's never just one right answer. You just need to make sure that your graph hits all of these points here. All right, let's do another example. I want to determine the intervals on which the function y equals x squared natural log of x is concave up and down, up or down, and then I want to determine any points of inflection that occur here. So we need the second derivative for all of that. Now this function is defined for all positive real numbers, and it's a product of two continuous functions, so it's going to be continuous on all positive real numbers as well. So that means when we're looking for inflection points, we don't need to think really hard about the continuous part of this definition. It's going to be there. What we're more interested in is where that second derivative is equal to 0. So let's find that second derivative first. Y prime, this requires the product rule. So x squared's derivative is 2x. Then I have the natural log of x. The derivative of the natural log of x is 1 over x. So this gives me x squared times 1 over x. Or to simplify, I get 2x natural log of x plus x. Okay? Now I need the second derivative. So let's take the derivative of that. The derivative of 2x is just 2, and I have my natural log of x. Derivative of the natural log of x, I'm going to have 2x times 1 over x, and then the derivative of plus x would just be plus 1. Simplify here, I can cancel these x's, leaving me with 2 plus 1, that's 3. So I get 2 natural log of x plus 3. And we want to set this equal to 0. Okay? If this is equal to 0, this is easy to solve for x. I get x equals e to the negative 3 halves. It's like 3 steps, 3 very short algebraic steps to get there. Okay? Now, remember what we're doing is we're finding where our second derivative is positive and where it's negative. And this value is the only value where the second derivative was equal to 0, but I'm also going to be putting a 0 here. And the reason for that is because, like we said at the beginning of this example, this function, since it has a natural log in it, is only defined for positive real numbers, which means this interval from e to everything to the left of e to the negative 3 halves doesn't just go to negative infinity. It goes to 0. Okay, it doesn't even get to 0 because it's not defined there, but everywhere between 0 and here is one interval. Everything from here to here is another interval. Now, you can do the test point thing here if you want. You can plug this into a calculator. You get something that's approximately, I think, 0.22-ish, and then plug in test points using that decimal approximation. Another thing you could do is take a look at your second derivative here. This function, 2 natural log of x plus 3, is just the natural log function with a vertical stretch and a vertical shift. There's no reflections there. There's no horizontal shifts left and right. So that means this function is going to look like a natural log function, which looks like that. And we just know that it's equal to 0 here at e to the negative 2/3 power. Okay? And this is not the graph of y. It's not the graph of the original function. It's the graph of this second derivative that we just found. Notice that to the left of e to the negative 3 halves power. I wrote that wrong, 3 halves. The function is negative down there. So y double prime is negative. And then to the right of that value, it's positive. Y double prime is positive. So that's another way of just, rationally working out where the second derivative is positive and negative. So what we're seeing is a function where the second derivative is negative on this interval, positive on this interval. So we have a change of concavity, which means there is a point of inflection there. Okay, so let's determine the intervals first. So concave, in fact, I'm going to use that notation. It's concave up on the interval from e to the negative 3 halves to infinity. Concave down on the interval from 0, e to the negative 3 halves. Now the point of inflection, the x-coordinate of that point of inflection is e to the negative 3 halves. Okay, but I do need a y-coordinate because it's a point, so we need an x and a y, and the y-coordinate comes from plugging the x-coordinate back into the original function. So let's do that really quick. That's plugging that in for x. I'm going to have x, or e to the negative 3 halves squared times the natural log of e to the negative 3 halves. This is equal to e to the negative third, just using an exponent property. And then this is just equal to negative 3 halves. So I'm going to write that as negative 3 halves e to the negative third power. Again, don't worry about decimals, just leave things in terms of e. Okay, so that answers that one. Okay, last page. So we have one more test that we're going to talk about for finding local extrema, finding local maximum values, local minimum values. We've done the first derivative test already. And in my experience, the first derivative test is the most popular one. People tend to use that one the most because the second derivative test requires you to find a second derivative. I think a lot of students look at that and think, oh, well, finding a second derivative means doing more work. But there are a lot of cases where the second derivative test is actually easier. So it's good to know both. I'm going to cover this one here. The second derivative test says that if f double prime is continuous near some number c, if f prime of c equals 0 and f double prime of c is greater than 0, then f has a local maximum at c. If f prime of c is equal to 0 and f double prime of c is negative, so less than 0, then f has a local maximum. Did I say maximum here? Minimum here, maximum here. The reason for this is in both of these conditions, we're saying that f prime of c equals 0, which would make it a critical number. Okay, so in the first case, if c is a critical number and f prime of c is greater, f double prime of c is greater than 0, then we're looking at something like this. Okay, critical number because I have a horizontal tangent there, concave up because f double prime is positive at that number c. Notice the concave up part of that is what makes this value a minimum. Similarly for part B, if I have a horizontal tangent here, which means I have a critical number, and if the second derivative is negative there, which means concave down, from this picture you can see that that would create a maximum. Okay, so this is an immediate consequence of what we just talked about with that concavity test. So what I want to do now is find the local maximum and minimum values of this, of y equals 200 plus 8x cubed plus x to the fourth. So in order to do that, what we need to do is find the first and second derivatives. So what is the first derivative of this function? Y prime is equal to 24x squared plus 4x cubed. Okay, now we still need to set this equal to 0 and solve it because the second derivative test involves the first derivative here. We have to find critical numbers first. So I'm going to factor this, 4x squared times 6 plus x, set that equal to 0. That would mean that x is either equal to 0 or negative 6. Those are the two critical numbers that I'm getting out of this polynomial. Next, let's take a second derivative, y double prime, and I'm going to get 48x plus 12x squared. okay? Which, if I wanted to, I could factor that as well. I could write that as 12x times 4 plus x. Now, these two critical numbers, what I want to do is plug them into my second derivative to determine whether we have a maximum or a minimum. So if I take y prime and I plug in x equals, or y double prime, plug in x equals 0, I get 0 in my second derivative. From the second derivative test, that's inconclusive. We don't know if we're looking at a local minimum or a local maximum there. It's not telling us either way. So we're going to leave that one alone. We'll use the first derivative test for that guy. Y double prime evaluated at x equals -6, my other critical number. I don't need to get an explicit answer. I can just use that positive negative logic as we've used before. So for example, 12 times -6 is a negative number. 4 plus -6 is -2, another negative number. Negative times negative is positive. So regardless of the actual value of this thing, the important thing is that it's positive. So what does that mean? Well, that means that our function is concave up at x equals -6, which means we're looking at one of these types of cases when x equals -6. We have a minimum there. Okay, so I have a local minimum at x equals -6. We'll figure out what that local minimum is in a moment, but I want to return to this guy. My second derivative test didn't give me enough information, so what I need to do is go to my first derivative test. We've already found the critical numbers for our first derivative, 0, -6. And now I just need to use the increasing-decreasing test to figure out where is this function increasing, where is it decreasing. And since we've already found that -6 is a local minimum, we don't need to worry about this interval over here. I just need to know what's happening on either side of 0. So if I plug in a negative number into my first derivative, let's say this guy right here. Let's plug in something less than 0, so let's plug in like a negative... hang on one second. Is that where I want to plug it in? Yeah, let's say I plug in a -1. Then I'm going to get a positive here. 6 plus -1 is positive, so that's positive. I get y prime being positive there. What if I plug in... Oh, you know what? I knew this looked weird. I put my numbers in the wrong order. Course, -6 is over there. Something felt weird about that. Okay, let's try this again. I plugged in a -1, and I found that I ended up with a positive first derivative. Y prime is positive. Okay, if I plug in a positive one, something to the right of 0, I'm going to get positive times positive again. Y prime is positive. So because we don't have a change from increasing to decreasing or vice versa, this is not a local maximum or minimum. Even though it's a critical number, it doesn't give us anything useful. Okay, so now I need to find what this local minimum is equal to. So that's going to, if I evaluate y at x equals 6, that's equal to 200 plus 8 times 6 cubed plus 6 to the 4th. Once again, I forgot to put this into a calculator, but I can do that really quick. So that's 200 plus 8 times 6 to the 3rd. Plus 6 to the 4th, 3,224. Okay, that's the only extrema, the local extrema that we got out of this thing. All right, now this example here, this final example, is asking us to sketch the graph of a function, and we want to use the information that we've come up with throughout this section. In a section that's coming up in chapter 4, we're going to look at this in more detail, sketching graphs using all of this information, but this is kind of a preview of sorts. So when you're curve sketching, there's different things that you look for. And what we're primarily interested in right now is the increasing, decreasing, and concavity and stuff like that. I also want to pay attention to the domain. So notice in this function I have a polynomial here minus a logarithm here. So the logarithm is going to restrict the domain. The domain of this function is only the positive real numbers because of where that natural logarithm is showing up. Okay. Another thing that we tend to want to look for in graphs of functions is x and y intercepts. Now the tricky thing about this particular function is that in order to find an x-intercept, there's no y-intercept because this function is not defined at x equals 0, but in order to find an x-intercept, I'd have to plug a 0 in for y and then solve for x. But because this function is a mix of a polynomial and a logarithm, there's really not a good algebraic way of solving for x in an equation like that. At the end of this chapter, we'll talk about Newton's method, which is a technique for approximating zeros of functions. But right now we don't have that technique, so I'm not going to worry about the x-intercept right now. But what I will do is look at concavity, increasing, decreasing, critical numbers, points of inflection, all of that stuff. So let me start by looking at y prime. What is y prime? Well, it's equal to 1 minus 1/3 x, and then this is equal to minus 2/3 times 1 over x, because that's what the natural log of x, its derivative, would be. So I'm going to set that equal to 0. And then what I'm going to do to solve this, I'm going to multiply everything by x and everything by 3x, because I want to eliminate the 3's as well. So if I multiply everything by 3x, let me actually start with this. Let me multiply by negative 3x, because I want this to be a positive term right here. I'm going to get x squared from this term. Negative 3x times 1 is negative 3x. And then negative 3x times negative 2/3 over x is going to be positive 2. Okay? That's factorable. X minus 1, x minus 2 equals 0, which implies that x equals 1 or 2. Okay? So what I'm going to do is set up a number line, 1, 2, and do what I've done before with test points. Okay, I'm going to plug 0 or something less than 1. I can't plug in 0 because I know that 0 is not even in the domain of this function, so I have to stay between 0 and 1. But let's see. I'm going to do a little bit more with this actually. So this is equal to 1 minus x over 3 minus 2 over 3x. I'd like to get a common denominator and multiply all of this stuff, or put all of this stuff together. So this is equal to 3x over 3x minus x squared over 3x minus 2 over 3x, which is equal to this negative x squared plus 3x minus 2 over 3x. That's the opposite of this. So I could write that this way. Negative x minus 1, x minus 2, all over 3x. The reason I'm doing that is because it's going to be easier to use my, easier to check for increasing or decreasing using this version of that derivative. So let's say we picked a number like number like 1/2, something between 0 and 1. 1/2 minus 1 is negative. 1/2 minus 2 is negative. So I have negative times negative, which is positive, over 3 times 1/2, which is positive. Positive over positive is positive, but then this negative out here means that's negative. So y prime is negative there. Now let's pick something like 1.5. 1.5 minus 1 is positive. 1.5 minus 2 is negative. I have negatives times positive, which is negative. This will be positive. Negative over positive is negative. This negative out here changes that to positive. Okay, and then finally, pick something bigger than 2, plug it in. You'll find that y prime is negative in this case. Okay, so this means that we are increasing on the following intervals, increasing on 1 to 2, the interval from 1 to 2, and that's actually it. So on the interval 1, 2. We're decreasing on 0, 1, and 2 to infinity. Okay? All right. Next up, we want to look at the second derivative, y double prime. So looking at, we'll look at this version of our function. If I take the derivative of this, I'm going to get negative 1/3. What is this going to be? This is negative 2/3 times 1 over x. That's going to be plus 2/3 times x to the negative second power. I'll just write it that way. Let's set that equal to 0. Actually, let's do this. Let's write it as negative 1/3 plus 2 over x squared, or sorry, 2 over 3x squared. Get a common denominator, add things up. So this is equal to negative x squared plus 2 over 3x squared. Okay. If I set that equal to 0, then that's the same as this numerator equaling 0, which is the same thing as saying x squared equals 2, so x is equal to plus or minus root 2. However, negative root 2 is not in the domain of this function, so we only need the positive root 2. Okay? Now, once again, we're going to break this thing up into these intervals. And I'm going to plug things into my second derivative. Let's use this version of the second derivative to do that. So no matter what, my denominator is going to be positive, because it's something squared down here times a positive 3. Here, if I plug in something greater than root 2, let's say 10. 10 squared is 100. Negative 100 plus 2 is negative 98. So I have a negative over a positive, which is negative. My second derivative is negative here. That means we're concave down there. Okay? My first derivative, my first interval is 0 to root 2. If I pick something smaller than root 2, like 1, for example, negative 1 squared is negative 1 plus 2 is positive 1 over a positive. That's positive. So that means we are concave up on the interval from 0 to root 2, concave down on the interval root 2 infinity. Because there's a change in concavity and because this function would be continuous at root 2, we also have a point of inflection at root 2. And what is that equal to here? Root 2, I'm going to get a decimal for that actually. Let me plug that in really quick. So that's going to be square root of 2 minus 1/6 times 2, so that would be minus 1/3 minus 2/3 natural log the square root of 2. What am I doing wrong here? So that's approximately 0.85. Okay, sorry, I kind of disappeared there for a second while I worked something out. So what I was doing here was just finding the y coordinate of this point of inflection by plugging root 2 into this. I used a calculator to do that. I got approximately 0.85. So I'm going to need a different sheet of paper to do my graph. But I want to sketch something that has all of this information on it. So we'll kind of go back and forth here. Like this. Our function is not defined to the left of the y-axis because the domain is 0 to infinity. I have an actual point that I know exists on this graph, root 2, 0.85-ish, right? So right there is going to be this point that's on the graph. Now, we know that we are concave up from 0 to that point and concave down from that point onward. And we also know that we're increasing on the interval from 1 to 2. 1 is going to be over here somewhere. 2 is going to be over here somewhere. Root 2 is between those two values. Okay? So I'm actually going to do this to kind of separate things out a little bit. Those are not vertical asymptotes. It's just helping me with where we change from increasing to decreasing. So we're decreasing on 0, 1, and we're also concave up there. So that means that I'm going to be doing something like this. Okay? Notice I'm decreasing, but I'm concave up. I'm concave, let's see. Oh, and then we switch. Oh, I'm going to change that actually. We switch from decreasing to increasing at 1. So actually, I'm going to want something kind of like this. Okay? Because notice I'm still concave up this entire time, because I need to be concave up until I get to root 2, but I'm decreasing and then increasing once I get past 1. Now I know I have to hit this point of inflection right here. Okay? That's given by this point of inflection. And then as we pass through root 2, we switch from being concave up to concave down. But I'm still increasing until I get to 2. That's what this is telling me. So I'm concave up, but I need it to start looking concave down now. See how it kind of switches from up to down there, making that my point of inflection. And then after 2, it's supposed to decrease all the way to infinity. So it's decreasing after that point. Nothing in this told me that I had a horizontal asymptote or anything like that, so I would expect this to just continue decreasing downward like that. Okay, and again, we weren't able to find the x-intercept because we don't have a technique for that quite yet. I am expecting an asymptote or something there because we don't have anything to the left of that y-axis. So this is kind of a rough sketch. We're going to go into more detail about curve sketching, like I said, in a later section. But this will wrap up section 4.3 for us.